So first up this morning, we're joined by Kendra Nguyen, who's a rising sophomore at Pomona College. Kendra this summer has been working with Johanna Teske, and today she'll tell us about her project comparing compositional predictions for super Earths and sub-Neptune planets. Go ahead whenever you're ready.
Good morning, everybody. Thank you for joining me here today as I talk about my research on exoplanets. Let's begin with some background on the planets I am studying. The planets I'm studying fit into two categories, super Earths and sub-Neptunes. Super Earths are between 1 to 1.6 Earth radii, while sub-Neptunes are between 1.6 and 3 Earth radii. These categorization came from two reasons. One, internal evolution models show that super Earths are rocky, while sub-Neptunes may have a volatile envelope. The second reason is that from the graph here you see on the left, it's clear that the sizes fall into two groups, as you can see by peaks here. Here's Earth for reference at obviously 1 Earth radii, Neptune for reference at 3.8 Earth radii. The peaks occurring at about 1 to 1.6 Earth radii, and a second peak for sub-Neptunes occurring at about 1.6 to 3 Earth radii. So what's so interesting about these planets? Well, the Kepler mission revealed that there was an abundance of 1 to 3 radii planets outside of our solar system. Interestingly enough, our Milky Way does not have these. A major question in the exoplanet field is why? The two questions I have been trying to answer this summer is one, what accounts for density differences in the exoplanets? Hopefully, by learning more about the composition, we can find out what accounts for the lack of 1 to 3 Earth radii planets in our solar system by learning more about differences in formation and evolution. The second question I've been trying to answer is how effective are these codes at predicting exoplanet composition? I have been studying 22 planets this summer from the Magellan Test Survey and the JWST GO proposal, written that my advisor, Johanna Teske, was a co-principal investigator for. These planets were chosen because we will be able to test our predictions for these planets against observational data from the JWST proposal. The other reason we chose these planets is because their masses were obtained from a program designed to minimize bias. You can see here on the right is the graphs of our planets in our sample against a background of confirmed exoplanets to NASA Exoplanet Archive. The planets are the same in both graphs. The only differences was that the masses were obtained from two different Python packages, Radville and Juliet, in order to see consistency in the masses. I used two codes this summer in order to obtain the composition predictions. First up is MDN exoplanets, which predicts the planet's gas, ice, mantle, and core densities to hopefully help us answer questions about the layers. And secondly, we have Exoplex, which answers questions about the mineral and water composition to help us answer questions about what the layers are made of. I'll start by going into more detail about how we sought to determine the characteristics of the layers of the planets. Let's lay down some basics. MDN stands for Mixture Density Network, and these are models that are composed of a neural network and a probability mixture. The author of the code used a data set of 900,000 synthetic planets to train the networks to predict 4 layers for the planets: an iron-rich core, a silicate mantle, an ice shell, and a hydrogen to helium envelope. The author of the code trained a neural network with 70% of these planets and then validated the results with the remaining 30%. Here's an illustration to help us better understand how the code works. First up, we have the training set of the 900,000 synthetic planets. This kind of serves as a set of information. Next, we have this here, which is the neural network, which acts as a filter to help us determine what the categories of these inputs fit into. And third, we have the mixture model, which tells us the probability of the features. In this case, what is the probability of the hydrogen to helium envelope, the silicate mantle, the iron-rich core, and there being a high layer pressure of ice. Just to give you an example of what MDN results look like, let me show you the result for Earth. Here on the left, we have the the y-axis, which tells us the probability density. The lack of units tells us that this is only good for relative comparison to other graphs. We can't tell the units. We can only look at like how the details of the lines of the graphs. Secondly, the x-axis tells us the percentage of how thick the layer is, as I mentioned before. Here's how to read the graph. The purple peak here signifies that there's a high relative probability of Earth having a near relative zero thickness gas layer. And this black peak here signifies that there's a high relative probability of Earth having a high relative thickness of a core layer. And this here shows us mantle and ice. And pretty consistently throughout all our planets, we have it's generally relatively low probability of thickness for the ice and mantle layers. I do have to warn you that the model has high uncertainty due to the lack of a fluid Love number. The Love number is a measure of the planet's rigidity. We had to choose this model because we do not have the fluid Love numbers for our planets. On the left is the planet without the Love, is the calculation prediction for Earth without the Love number. You can see here that there's high uncertainty here, where this is the actual prediction, actual thickness for Earth, whereas this here is MDN's prediction. And with the Love number, it greatly improves accuracy, with this being MDN's prediction and this being the actual known result for a core, Earth's core. With that said, I separated the graphs into 4 categories based on core thicknesses. Here are the different components again from the Earth sample. So first up, I looked at the core thickness. Here's the peak. I determined the peak to be less than 0.5. So this means that peaks at less than 0.5 would go into category of core thickness of less than 0.5. Peaks at about 0.5 would go into category of core thickness of about 0.5. Peaks greater than 0.5 will obviously go into the category of core thickness greater than 0.5. And irregular graphs just go into their own category because obviously they don't have a peak like the other categories do. Secondly, here are the probability predictions for the gases. So for the first one here, we can see that we interpret this since it can go straight up instead of kind of asymptotic like this one, as this saying that there is a non-zero gas probability of about 0.25, but this here does mean that it has zero gas probability. And same with these other ones as well. Okay, so here's a graph I made summarizing the results for these exoplanets. I wanted to look for correlations between the temperature, density, and the thickness of the cores. So on the y-axis here, I have equilibrium temperature, and on the x-axis, I have the density in units of Earth density. The purple here represents planets in the categories of about 0.5 Earth, 0.5 core thickness. In black is the less than 0.5 thickness. Yellow is greater than 0.5 thickness. And then the ones that are brown are irregular. And I'll go into the non-zero gas probability in a different slide. So an interesting observation is that there is a clear distinction between planets of less than 0.25 Earth density, as you can see here, and greater than 0.5 Earth density at about 0.5 core thickness and greater than 0.5 core thickness at about 0.25 Earth density. Secondly, I also wanted to look at if there was any trends among non-zero gas probability. Like I said earlier, these are the graphs that have predict a non-zero gas. You can see interestingly here that most of the ones that have a non-zero gas probability fit in the less than 0.5 core thickness category. Next, I wanted to see if there was any trends among the layers and the possible minerals that they could be composed of. To do this, I used Exoplex. Exoplex is a code developed to study TRAPPIST-1 planets. The TRAPPIST-1 planets are 7 planets found in the habitable zone of the TRAPPIST-1 star. These planets are great for studying because they are Earth-like terrestrial planets, and we know them well. We actually have a study in 2018 that tells us their density. What the Exoplex code does is tells us the planet mass given the input radius and our assumed composition for them. Our assumed composition for them consists of gases for iron to magnesium, silicon to magnesium, calcium to magnesium, and aluminum to magnesium. So why are these ratios specifically? Well, these ratios are first off present in terrestrial planets. They're good for studying Earth-like planets then. The second reason is that they're found across 10 planets. But Earth-like isn't just about studying what planets are made of. It's also about studying their properties, because to be able for a planet to be Earth-like, it also needs to have similar plate tectonics to Earth. So these minerals can impact a planet's melt properties, viscosity, elasticity, and its plate tectonic activities. Moreover, the iron to magnesium ratio can affect a planet's core size. This can influence how the heat flows from the core to the mantle. Unfortunately, we did run up to some problems with Exoplex. Since the code was designed for TRAPPIST-1 planets, we found that when we ran our radius and map through for our planets, the code seems to bug out. Currently, it can only accept radiuses up to 1.6 Earth radii, and the greatest mass it can predict is up to 6.6 Earth masses. This leaves 15 out of our 22 planets currently untestable. What we did want to do once we had the MDN and Exoplex result is compare them to see if there were any trends between the two graphs. So we have a graph I made for summarizing the Exoplex results here, and a graph I made and the graphs from the MDN exoplanets results on the right. You can see that all these graphs so far are from the greater than 0.5 core thickness category. So we can't currently draw any conclusions given our limited sample, but we do see, as expected, an increase in iron to magnesium ratios as the Earth density increases. And you can't see all the graphs here because you can't see all the dots here because some of the dots do overlap each other. With that being said, my future questions for this project are: what composition accounts for non-zero gas probability in some less than 0.5 core thickness exoplanets? I would like to explore this question by looking at the JWST atmospheric observation results. My second question is looking for a way to categorize the irregular graphs better. Since previously it seems like the regular graphs are spread out, I was wondering if maybe if I look at the graphs again, can we separate them into 0.5, or can we separate them into greater than or less than 0.5 categories? My third question that I would like to wrap up this project with is: what trends between mineral and core compositions are evident between MDN exoplanets and Exoplex? So this can be done once I finish debugging the code and with the author of the code. Thank you for listening to my presentation.
All right, very nice job, Kendra. Do we have questions for Kendra about her presentation? Sonata, do you have a question?
Yeah, I did have a question. Thank you so much, Kendra, for presenting. It was a great presentation. I had a question about something you said on slide 13.
Okay.
Yeah, so when you were talking about like, I think probabilities, I got a little bit confused because I was trying to figure out like, how is it that you determine the probabilities? Because some of these, like there was like a very high probability density of having a very low core thickness, but then you said something, I got a little confused because sometimes there were peaks in other places, and like you would say, like if there was a very high probability density, like towards the very left side of the graph, sometimes you would say like there's a very high probability density of a relative thickness, but then it would be like further along. And so I was kind of wondering, like, how are you explaining the probability density and how is that relating to each relative thickness? Maybe I just misunderstood.
Yeah, thank you for asking. No, it's definitely something that's a little confusing. So for this graph, you can see that it seems to approach very straight at 0. So based on, there's another graph we had for Neptune where similar to the Earth graph here from the code, it showed 0 for Neptune as well. But we know Neptune obviously is a gaseous planet. So that meant that this has to be the prediction for the planet instead of this. So this is the peak instead of this one. But for this one, since it's similar to Earth, where the line here kind of approaches this as an asymptote, we determined this to say that the planet has 0. Earth is the highest probability of the gas layer is 0.
Okay, thank you. That really clears it up a lot. Thank you so much.
Wonderful. Do we have any other questions for? Last call. All right, very nice presentation, Kendra.